Okay, folks, I will make a start. Where we got to on Monday morning was we gave a sort of demonstration of the superposition principle, or a demonstration of why it might work. And essentially we got to this point where we stated the superposition principle, which just says in any linear resistive network, so all the circuits that we look at, the voltage across or the current through any resistor or source may be calculated by adding algebraically all the individual voltages or currents caused by the separate independent sources acting alone, with the other independent sources replaced by short circuits, independent voltage sources replaced by short circuits, and the independent current sources replaced by open circuits. So that's a mouthful, but it is a very helpful tool for us as a way of simplifying more complicated circuits. So the best way to get a real feel for how it works is to look through a couple of examples. So the first problem here is I want to know the current through the 9 ohm resistor. Now it is possible that I could solve that problem as it is just using Kirchhoff's voltage law and current law if I desired. What superposition is just another alternative that you could consider using in some situations. And the idea is that you would look at that current caused in that 9 ohm resistor by each of the sources in the circuit individually, then you add the results together. So let's see how it works. There's our problem. My first issue is I want to see how much current is caused in the 9 ohm resistor by only the voltage source. If I'm looking at only the voltage source, I need to zero the current source. So I need to make sure that the current through the current source is zero. And if you think intuitively, how can I make sure there is no current going through something? I make it an open circuit. So if I have an independent current source that I want to zero, I just make it an open circuit. So I imagine it's just not there. So when I'm assessing the impact of the voltage source, all I need to do is solve that circuit. And if you look at that, you can start to see why superposition might be a good thing, because that circuit looks hopefully relatively simple. Because you've just got a voltage and 2 resistors in series. So Ix, due to the 3 volt voltage source, would be just that 3 volts divided by the total resistance it sees, which is 6 plus 9. So I've got 3 divided by 15, which is 0.2 amps. Do I need to clarify anything on that? It's Friday afternoon, I'm in a good mood. We're all happy. Cool. All right, so I go back to my circuit and now I say, well, what is the current through the 9 ohm resistor due to the current source? So again, the thought process is that I would need to zero the voltage source. How do you make sure something has 0 volts across it? You make it a short circuit. So For a voltage source that I want to 0, I short circuit it out. Current source, I want to 0 it, I make it an open circuit. They're the two things you need to remember. Now I look at the problem and say, okay, in this circuit, what is the current in the 9 ohm resistor due to the 2 amp source? Now it's a little bit more complicated than the previous one, but if you're sort of up to date, you might recognise that as a current divider problem. So in this case, the current through the 9 ohm resistor would be the 2 amps multiplied by the resistance of the branch that I'm not interested in, 6 ohms, divided by the sum of the two resistors. So I would have 0.8 amps there. Now if you weren't completely confident that was a current divider, you could say, well, I've got two resistors in parallel. I could work out their equivalent resistance, multiply it by 2 to work out the voltage, then divide by 9 ohms to get the current. So that would work too. Either result would work. So now, if I want to know the total current through that 9 ohm resistor, I just say, well, it's the current due to the 3 volts plus the current due to the 2 amp source. So I've got 0.2 plus 0.8, which gives me a total of 1 amp. So superposition has hopefully let me take a more complicated problem and reduce it to some equivalent, simpler problems. Let me ask again if there's any questions. Going, yes. Yep. Yes, so I'm imagining that I want my voltage source to be 0, and the way I absolutely ensure that a voltage is 0 is put 0 resistance in there. Ooh. One more example. So here is a slightly more complicated circuit. This one has 3 sources in it. Again, what I want to find out is a current I4. Now, I could use Kirchhoff's current laws and voltage laws to solve this, but it would be a little bit more difficult, this one, than the previous one. So this style of problem, because of the additional source and the extra loop, makes me think superposition is well suited to it. So again, start with the circuit, pick one of the sources, 3 milliamp source, so that means I need to 0 the other sources that are in the circuit. The other sources are voltage sources, so they're going to become short circuits. So the circuit I need to solve is that one. In that circuit, hopefully you can see I've got 3 resistors in parallel, the 2 kilo ohm, the 1 kilo ohm, and that 3 kilo ohm, even though it's drawn up the top, is in parallel with the 2 and the 1 kilo ohm resistors. So again, what that circuit looks like is a current divider with 3 branches. So the first thing, because there's 3 branches, not 2, I need to work out the equivalent resistance of those 3 branches. So I've got 2 in parallel with 1, in parallel with 3. The way I do that is 1 over R equivalent equals 1 on 2 plus 1 on 1 plus 1 on 3. At this point, I break out my calculator because it's just too much trouble to try and think through that and do it in my head. It's Friday afternoon, after all. And you get the equivalent resistance is 0.54 kilo ohms. Once I know the equivalent resistance, I can go to my current divider formula where I have more than 2 branches, and it's just the current I times the equivalent resistance divided by the resistance of the branch that I'm interested in. And again, I know I've said this before, but hopefully you can say, well, I see where that formula comes from, because I times the equivalent resistance tells you the voltage across the parallel branches, divided by RK, and it tells you the current in the kth branch. So we whack in some numbers. 3 milliamps times 0.54 divided by 3 gives us 0.54 milliamps due to the 3 milliamp current source. Pausing, shout out if you've got questions. I want you to be happy. Cool. 2 volt source. So we're looking at the voltage source up the top. So we've got a 0, the current source, and the 10 volt source. The current source becomes an open circuit, and the 2 volt or the 10 volt source becomes a short circuit. Now here I want to work out the current I4, and if I start by sort of looking at the circuit, I can see that the 1 kilo ohm and the 3 kilo ohm resistors are in parallel, and they're in series with that 2 kilo ohm resistance. So if I start with that 1 kilo ohm and 3 kilo ohm resistor, I can work out their equivalent resistance, which is just 1 times 3 divided by 1 plus 3, which is 0.75 kilo ohms. So that's suggesting that those 2 resistors there could be replaced by a 0.75 kilo ohm resistor. Therefore, the total resistance is now 2 plus 0.75. Therefore, the current from the 2 volt source, so it's the current here, is 2 volts divided by 2.75, which is 0.72 milliamps. So the 0.72 milliamps flows through the 2 volt source. It flows through the 2 kilo ohm resistor because it's in series with the 2 volt source. But it will divide when it gets to the 1 and the 3 kilo ohm resistors because they're parallel paths. So again, I'm using the current divider expression to work out how that 0.72 milliamps splits between the 3 and the 1 kilo ohm resistor. So I just go I times the total resistance divided by RK. Now you could have used that 2-leg current divider expression. I suspect the reason I used this method in this case was that I'd already worked out what R1K in parallel with R3K is. So I already had that number. So I4 due to the 2 volt source will be 0.72 milliamps multiplied by 0.75 divided by 3K, which is 0.18 milliamps. Any questions there? As I'll keep saying, and I'll keep saying it, it's important that you be doing some of these problems yourself in the tutes, because it's easy to watch someone else do it. You don't get to watch me in your final exam. All right, one more problem, the 10 volt source. Zero the other sources, so we're starting to see the pattern here. The voltage source is a short circuit, current source is an open circuit. Now I've got to analyse this circuit and try and work out what the current I4 is. So effectively, what I need to know is what is the equivalent resistance of that circuit, where I've got a 3 kilo ohm in series with these 2 resistors in parallel. If I've got that total resistance, that should tell me what I4 is. All right, so the 1K in parallel with the 2K is just 1 times 2 divided by 1 plus 2, which is 0.67 kilo ohms. The total equivalent resistance is 3 plus that 0.67 kilo ohms. Therefore, I4 will be 10 volts divided by that total equivalent resistance. Except you will notice that I put a minus sign in there. And if you look at that circuit where I've got a voltage source and resistors, you would expect that positive current would come out of the positive terminal moving in an anti-clockwise direction in that circuit. Here, I4 is defined as going in the clockwise direction, so we recognise that by putting in the minus sign to suggest that, well, actually the current is going in the opposite direction to what I4 indicates. So it's minus 2.72 amps. So last step is to just add them all up. So I've got a 0.54, a 0.18 and a minus 2.72. They'll add up to give you minus 2 milliamps. I certainly can. You want the whole slide? That one? Yep. I'm perfectly happy for you to shout at me and make me go back if I'm flicking through too fast. Tell me when you're good. Yeah. So the question was, for those watching at home, how do I know when to use superposition or Kirchhoff's laws? There's no right or wrong answer, so I can't give you a definitive use superposition in these ones. The place where I would think about it is where I've got more than two sources. If I've got two sources, like in example 1, there's a possibility that I could do it just as quickly with Kirchhoff's current law or voltage law. But if I'm getting to 3 sources, I'd be thinking superposition is probably the thing I would look at. But certainly, particularly when you're looking at my work solutions, always bear in mind that, you know, there are other ways to do the problems besides the way I did them. So any one of these problems, I could expect that, you know, you might present 4 or 5 different solutions and you could all be right as long as you get to the same numerical answer. All right, everyone's got that? I can bounce around and yes? Yep. So you're talking about a scenario where I might have a voltage source and a current source in series? And yep, okay. Yeah. So if the current source was sitting in here and you made it a 0, which is an open circuit, then your conclusion would be that that voltage source doesn't produce any current in I4. Yep. All right, I will keep moving on. I don't know if I'll get through all of this lecture, but we'll hopefully find a sensible place to stop if we don't. First one, this one is for the women in the room. I was asked to draw it to your attention. It's just a lecture networking event that's coming up in a week or two's time. I just wanted to reiterate that women are very welcome to attend that event. If you want, it's in my slides, so if you want to do the scan thing, it is there. Okay. Quiz 1. Second reminder is next week, quiz 1 will be on. It is an online quiz. And the quiz will be open between 8 a.m. Thursday morning until 8 p.m. on Friday evening. So students will have 1 hour to complete the quiz, and the timer starts from the moment you log in and go, your hour starts. Now, students in the class who have supplied reasonable adjustment plans that require their quiz length to be adjusted, that will happen automatically, providing I have the reasonable adjustment plan. So if you've held off sending it to me, I need to get it by next Wednesday so that I can make that adjustment. After Wednesday, there's nothing I can do except to say, well, I can make the adjustment for future ones if you give it to me. The quiz is only going to cover material from the commencement of the course up to including Kirchhoff's current and voltage laws. So that would include the things we did as KVL, KCL examples on Monday morning. So that's where the line is being drawn. All the problems we'll be able to solve with the things that you've done up to that point. No superposition. I've just got to go through and check, but certainly if there happened to be a problem in there with 2 sources, you can do it using Kirchhoff's voltage and current laws. You could use superposition to also solve it, but you certainly can solve it using not superposition. That's the thing I'll guarantee. No, there's no upload work solutions. So it's just purely multiple choice primarily. There may be one or two value questions where you need to put in a number. Now, on the put in a number questions, pay careful attention to the units. So if it asks for an answer in kilo ohms and the answer is 1 kilo ohm, put in 1. Don't put in 1,000, put in 1 for 1 kilo ohm. So do be careful with that. The questions are randomised, so you will each see different sets of questions, but they'll be very similar. So the questions sit in pools of similar questions, and when you get to question 1, you get one question from the pool associated with question 1. So don't expect that you will see the same questions as your friend. You'll see slightly different questions. So that is the quiz. If anything goes wrong, don't panic, just send me an email and we'll sort it out. So usually there's someone whose internet crashes the second after they hit go or something. Just let me know and we will sort it out. Any questions on quiz 1? Cool. Then what I want to talk about now is real voltage and current sources and how we might transform from a voltage source to a current source. So at the moment, all you've seen are voltage and current sources and resistors, and the voltage and current sources that you've seen are ideal. So if I look at the current source, it delivers a constant current, and it will do that regardless of the voltage across it. Now that device does not exist in reality, because if you think, if I could let that voltage be as big as you want, the current times voltage would get very big, so you would have to have a very, very big power source associated with it. Can't physically happen. So our notion of an ideal current source is very much ideal. Likewise, our voltage source, we've assumed delivers a constant voltage regardless of the current across it. When we come to real voltage sources and current sources, we quickly discover that you can't deliver unlimited current or voltage because you would need unlimited power. So real voltage sources are frequently non-linear, and the example I'll give you is your bench power supply, where you have a voltage knob and you have a current knob. And what that voltage source will do is something like this. So it will provide constant, in inverted commas, voltage up until some current limit, which you've set with your current limit knob. And if you try and draw more current than that current limit, the voltage will decrease until it eventually reach 0. So in that current limit region, it looks more like a current source. So there's that sort of non-linearity in a bench supply. But the other thing to note is even in that voltage mode, you'll notice that the line there is not perfectly vertical. In the current mode, that line is not perfectly horizontal. What you're seeing is that the voltage does drop, a little bit as the current goes up. The current drops a little bit as the voltage goes up. So for those reasons, what we will introduce is what I'll call a non-ideal voltage source and a non-ideal current source. And the main characteristic I'm trying to represent is the fact that as my voltage source loads up, the voltage gets smaller. The way I represent that is by including a series internal resistance. So I've added a resistor in there. So if you think about that, as that current I gets bigger, we will drop voltage across that resistance. The more I, the more voltage. So the voltage I effectively see will be the internal voltage, which I'm still imagining is ideal, minus the drop across that resistor. So if I compare the voltage characteristic, if I had an ideal voltage source, the voltage would be fixed and vertical. Because of that resistor, the voltage drops as the current increases. And the slope of that line is effectively the way that's drawn, minus 1 on R internal. So putting an ideal voltage source and a resistor in series gives us a model of how a real voltage source might behave. Similarly, I can form a model as to how a real current source might behave. And the way I imagine that is that I have an ideal current source and a parallel internal resistance. Here, as the voltage increases, I will create current through that resistance, which will subtract from the current being generated by my ideal source. So as that voltage gets bigger, I get more current through that internal resistance, therefore I get less current at the output terminal. So again, my characteristic, I've got constant current from an ideal source, but with that resistor, as the voltage gets bigger, that current reduces. So again, what I've done is to make an equivalent circuit model that behaves like a real current source would. Now, if I look at that characteristic, you could imagine, because this is sloping downwards, that there will be a voltage big enough that would eventually make that current source zero. So it may be way over here, but if I keep making that voltage bigger, I'll eventually make the current zero. Similarly, if I look at that characteristic, if I keep making that current bigger, I expect that eventually this line is going to intersect somewhere up here, and that would make that voltage source zero. So that's what I've drawn here. I've gone current, voltage. There is an ideal voltage source. There is a real current source, and what I've done is to make my graph big enough so that there is a point where the real voltage source reduces to 0. And at that point, I'll call that current the short circuit current. So if I walked up to my battery and I put a short circuit across the terminals, the current that I would get is that short circuit current. Now, what I'm going to argue here is that if I started with an ideal current source that happened to have that short circuit current value, it would have a characteristic that looked like that horizontal red line. And I could argue the other way and say, well, if I started with that current source, but it was a real one, and I kept making the voltage bigger, that current would reduce to 0. So what that's kind of suggesting is that I could have a voltage source, real one, that looks and behaves exactly the same as a current source, real one, from an outside looking in terminal type of perspective. So that characteristic could belong to a voltage source, it could belong to a current source. So there is an equivalency there. So to try and reiterate that a little bit more, here in the left-hand corner I've got a non-ideal voltage source supplying a load. So it's a voltage source, a resistance and a load. The current in that circuit is just the voltage source divided by the sum of those two resistors, so that top equation there, Ohm's law. The voltage across the load would just be that current, V internal divided by R internal plus R load, multiplied by R load. So I don't think there's anything surprising there, I hope. Now I'm going to compare this to the bottom circuit and say, well, if I've got a non-ideal current source supplying some load resistance, the current that I would have going into the load is just the internal current multiplied by a current divider expression. And so I've got an R internal divided by the sum of the two resistors. Similarly, the voltage that I've got going across the load would be that current multiplied by the load resistance. Now, if I imagined a scenario where I set V internal to be equal to R internal times I internal, I would argue that those equations are exactly the same. So if I have a scenario where the internal voltage here is happened to be equal to the internal current there multiplied by this internal resistance, those two sets of equations are identical because that V internal replaces the R internal times I internal. That V internal replaces the R internal times I internal. So all that suggests is that those two sources there can be made externally equivalent, providing that relationship V internal times R internal is maintained. So as long as that's true, those two circuits look exactly the same externally. So if I put them in a black box and I just had two terminals coming out, I wouldn't be able to determine if I had the voltage source or if I had the current source, because they would behave exactly the same as each other. Now that is going to give us another tool that will help us to simplify problems. I'll do example 1 and check the time again. Suppose I wanted to find the current I. Now I could think of 3 ways I could do it. I could probably do a Kirchhoff's current law up here at that node, and it would head off and give me a solution. Alternatively, I could say, oh, I've got 2 sources. I could probably use superposition and consider the current due to the 9 milliamp source or the 3 volt source, and that would work. So if you're bored over the weekend, try it both of those ways and see if one's easier or not. One of the challenges of this course is that I do give you a set of tools that will solve problems, and you've got to learn the skill of picking the right tool to solve the problems. So it's worth trying out the different tools and seeing how they would work and the wisdom of one approach over the other. A third way I could do this is to use source transformations, and that's the way I'm going to do it here. So what I'm going to say is that I've got a 9 milliamp current source in parallel with a 5 kilo ohm resistor. That looks like a non-ideal current source. What it suggests is I could turn it into a non-ideal voltage source. So our source transformations say that that is exactly the same as that from the perspective of those 2 terminals. To make them all equivalent, all I had to do was make sure that the resistances stayed the same and the voltage value is equal to the current times the resistance. So I've transformed my current source into a voltage source. Now, why is that helpful? Because I can redraw the circuit and make it now look like that.
How do we determine what the dominance is?
Say that one again.
How do we determine what the dominance is?
I still do not catch it, sorry.
How do we determine what the terminals is? Like the positive and
Okay, very good question. I'm glad you asked that one. So the question was, how do I know that that plus and minus is that way and not turned around? And I would suggest that the polarity of that voltage source needs to be consistent with the direction of that current source. So that current source pointing up would have current naturally coming out of the top terminal. I want current to be naturally coming out of the top terminal in the same direction, hence I want the positive to be located at the top. Thank you very much for that question. It was a good one. All right, so I've put that in the circuit, and I would argue now that now I've got this series circuit, it's much easier for me to solve because it's now just a single loop. And I'm hoping if you looked at that, you'd go, oh, that's just a single loop. Kirchhoff's voltage law is probably a good thing to apply in that case. So the current I'm trying to work out is I. I just work my way around that loop, so I'm going clockwise, so I've got a minus 45. Because the current is flowing in a clockwise direction, the voltage across the 5 kilo ohm resistor is 5 kilo ohms times I, plus 4.7 kilo ohms times I, plus 3 kilo ohms times I, plus 3, will get me 0. And we can solve that to get I equals 3.3 milliamps. And I'm looking at how long example 2 is going to take. I feel it's probably better for me to stop there than to rush example 2. I'll do example 2 using more than 4 minutes on Monday morning. So is there any questions at that point? Going. Yes. Yep. Yeah, so my way of deciding that sign is I'm just trotting around that circle, and because I hit the negative terminal first, I put a negative. So when I hit the 3 volt, I hit the plus terminal first, so I put a plus. Yep. No other questions? I will stop there. Have a good weekend, and we'll see you Monday morning. Pleasure. Good idea.
Is that
Yep.
same thing, just in a different situation?
That works if you've got 2 branches.
Right.
If you've got more than 2 branches, I use that version.
What on a voltage division? It's very similar, it's just flip.
Yes.
Is that right?
Yeah, there is a beat in there. Yeah.
Well, yeah, I just thought I couldn't figure it. I was trying to make sense of the two.
Yeah. And you can show that is exactly the same as that.
Yeah.
In a 2 branch case.
Yep.
Because if you think what 2 branches in parallel looks like is R1 times R2 divided by R1 plus R2. Then you come along and you divide by R1, so you get that.
No, so I'm just trying to visualise it. So if I've got R2, they're equivalent. I mean, the denominator has to be R1 plus R2. But I've only got RK.
So we've got that scenario.
Yep.
And you're trying to work out that.
Yep.
So your R equivalent is that in parallel with that,
Yep.
which is R1 times R2, R1 plus R2.
Yep.
When you try and work out that current, it's I times R equivalent divided by R1, which is that formula. But if you
R equivalent, so you put that on the top.
put that in there, that R1 disappears,
Yep.
then you get left with that.
Yeah, you do.
Yeah, they're the same.
Right, no worries. Thank you.
Cool.
Can you go to the previous slide, please?
Which, this one?
Slide 12.
Let me get it back. The things that can't be seen.
Yeah, that one. There.
Yep.
No, there. Slide 12.
Slide, oh sorry.
Uh, how do you go from a parallel to a series?
So that's the whole thing of source transformations. From the terminal perspective, what we're arguing is that both of those circuits behave exactly the same. So if I look at their characteristic, both of those circuits will have that sort of characteristic. Sorry?
Both sides are same.
Say that one again.
Both sides are same. They are behaving the same. 12 flats of 12. Yeah.
Yep. So you could, for example, put a 1 kilo ohm resistor on both of those circuits, and I would argue that the current that you get in that 1 kilo ohm resistor in both of those circuits will be exactly the same. If you put a 10 kilo ohm resistor on both of those circuits, the current that you will get in that 10 kilo ohm resistor is exactly the same. So if you're bored for 10 minutes over the weekend, just try putting the same resistor on both of those circuits, and you should be able to demonstrate that in every case you'll get exactly the same current through that resistor, or exactly the same voltage across that resistor. And it's important you feel confident with that, because that's the whole point of this
Also,
lecture,
yes.
that those two circuits are the same.
Same.
Yep. Try it out. Yeah.
Trial and error.
And if I'm wrong, come back and say, Colin, you were wrong. I'll eat humble pie.
I actually want to ask you one thing.
Yeah.
Today is my first lecture. As I earlier told you in an email that I got a visa issues.
Yep. Okay.
I'm Darshil Patel.
Mm-hmm.
So I missed so many lectures
Yep.
and tutorials.
Yep.
So I'm looking forward if you can help me out with understanding.
Absolutely. So I'm hoping that you can catch up your missing labs,
Okay.
just in your normal classes. If it becomes problematic, and I don't think it will, that we might need to let you catch up in another class,
Okay.
we can do that. But I think you'll be able to catch up. Obviously, you can see all the recorded lectures, and you can see all the
On Canvas.
tutorials, solutions on Canvas. But, you know, if you do need extra help because you didn't see it, the explanation in the tutorial,
Actually, I was like trying to understand today, but I'm not getting it completely
Yeah.
because it was my first class.
yeah, no,
So I'm
no.
trying to get it.
Yeah, no, and that's fine. Just make sure you either ask the tutor
Okay.
or ask me. As in, you know, you're
Yeah.
very comfortable just coming and knocking on my door. I'm in building
No, no,
PA,
no, no.
or grabbing me after lectures, and yeah, because it's the sort of course where you've got to stay on top of everything.
Yeah.
If you fall behind, you just get further behind. So you need to get on top of everything early.
I'll try my best.
Excellent.
Thank you so much.
No worries. Glad you're finally here.
Yeah.
Welcome to Newcastle.
Thank you so much.
You too.